We're still on solving right angle triangles. On the screen here we can see two questions. The first one states a chord 6.2 centimeters long is 3 centimeters from the center of a circle. Calculate the radius of the circle. And the second one states a chord is drawn 5 centimeters away from the center of a circle of radius 13 centimeters. Calculate the length of the chord. Now, these two problems actually drags us into the circle. We are now going to look at how we can apply the Pythagoras theorem in solving problems that result in a right angle triangle in a circle. To do this, first, what is a circle and what is a chord? We need to know what a circle is and what a chord is. Right from our primary schools, we all know what a circle is. That a circle is simply a locus of points which are of all equal distance from a particular point. But what then is a chord? A chord is simply a straight line joining any 2 points on the circumference of a circle. So here we can see we have several chords, about 4 of them. This is a chord. It's joining 2 points on the circumference of the circle. Here again I have another chord. This is another chord. And likewise I have another chord there. Joining 2 points on the circumference of a circle. So a chord is simply a straight line joining any 2 points on the circumference of a circle. Now let's look at how we can arrive at having a right angle triangle. Here is a circle. I'll take a chord in this circle. We are going to consider the center of the circle to be somewhere there. Let me change the color of my marker to white. Let's say this is the center of the circle. If we have the center of the circle described there, we will then be looking at the perpendicular distance of that point, that is the chord, from the center of the circle. We are interested in that. The distance of the chord from the center of the circle. Now after that, we all know what a radius is. The length of this blue line represents what? The distance of our chord from the center of the circle. And we say perpendicular distance, meaning that this is a right angle. And that's our center. Now we all know that the distance from the center of a circle to any point on the circumference is the radius. So I can join this point to this, and that will serve as my radius. Surely you all agree. If you like, you can join these other two from the center of the circle to any point on the circumference, also a radius. And you will agree with me that here I have a right angle triangle. If I call that O, I can call this M, I can call this B. Sorry, let's put that back. OMB, you will agree, is a right angle triangle. And I can apply my Pythagoras here. I can say the radius, which happens to be the hypotenuse in this case, OB square, is what? The sum of the squares of the other two sides. The other two sides are OM square and the last one MB square. Let's advance, because that's our triangle. Let's look at something. Yes. Now some other thing I've not mentioned. The line drawn from the center of the circle, which represents the distance of a chord, this chord AB in this case. The line ON, we said it is perpendicular one. It is perpendicular to what? The chord. Apart from that, it also divides the chord into 2 equal parts. That means looking at AN and the distance between N and B, both of them will be equal. So we'll simply designate them as XX. So the length of the chord AB is a sum of what? X and X. So take note of that, that the line drawn from the center of the circle perpendicular to any chord divides that chord into two equal halves. Now with this information, armed with this, we can now proceed to solve the problems at hand. That's the conclusion there. We have triangle OAN, a right angle triangle. That's our right angle. Remember that this line is perpendicular. That's the right angle. So we have the square of the hypotenuse. The hypotenuse is OA. Square of the hypotenuse equals to the sum of the squares of the other two sides, ON and AN. So let's now address the two questions we have at hand. The first one states that the chord 6.2 centimeters long is 3 centimeters from the center of a circle. Calculate the radius of the circle. Let's look at the diagram of this. Look at the question and carefully study the diagram. We are told that the chord has a length of 6.2 centimeters. And this is our chord. Our chord here is AB from this point to that point there. 6.2. Now we have drawn the line from the center which represents the distance of the chord from the center, OM. And we also know that this line is supposed to divide the chord AB into two equal parts. So we divide 6.2 by 2 and it gives us 3.1. And that's how we have 3.1 for this length and also 3.1 for the other length. This question also states that the chord is 3 centimeters from the center of the circle, and that is well represented by OM. We are then asked to find the radius. Of course, you will agree with me that this is the radius. Applying our Pythagoras theorem, we can address this so quickly. Let me change the color of my pen to white. Yes, you will agree with me that this will be, the hypotenuse is OB. I'm sure some of you would have solved this already. That's impressive. You should be ahead of me. OM, look at the sum of the squares of the other two sides. And then MB, which means our radius OB square, which is not known, is equals to 3 square plus what? 3.1 square. If we have represented this properly, we are sure we are going to get our answer right. So that's it there. OB square is equals to 3 square plus 3.1 square, and that's 9 plus 9.61. And you play that down, take the square root of 18.61, we have that the radius of the circle is 4.31. That was very easy. I'm very sure. It couldn't be easier than that. Now the second question we have here states. A chord is drawn 5 centimeters away from the center of a circle of radius 13 centimeters. A chord is drawn 5 centimeters away from the center of a circle having a radius of what? 13 centimeters. Calculate the length of the chord. Calculate the length of the chord. Let's look at the diagram for this. We are told the chord is drawn 5 centimeters away. Again, we are using AB as what? As our chord. It is drawn 5 centimeters away from the center. So that represents our OM. Please, the color of my marker is white. Let's go to black. That represents this from here to M. That's the length or the distance of the chord from the center of the circle, 5 centimeters. And we are told that the radius of the circle, OB in this case here, is 13 centimeters. So that's our radius. We are asked to find the length of the chord. We are looking for the length AB from here to that point. How do I get this? From the triangle OMB, we can easily find this length MB, which is X. But remember we said that the line OM drawn from the center perpendicular to the chord divides the chord into two equal halves. So here I have X on this side, X on this side, both of them equal. If I can determine this x or find the value of this x, I simply multiply by 2 and that will give me the length of my chord. I'm sure you agree. So let's look out for that. Here we have that the length of the chord is what? AB, which is 2x. Fine. We have agreed to that. Now considering the triangle OMB, which is here, and using Pythagoras, you will agree that the square of the hypotenuse OB square is equal to the sum of the squares of the other two sides, OM square, MB square. That's our OB square. Of course, substituting values, OB is 13, so that's 13 square equals to 5 square plus MB square. Remember, the 5 is what the length, the distance of the chord from the center of the circle. Substituting there, or sorry, let's evaluate. This is 169, 13 square, that's 25. Rearranging, we have 144 equals to MB square, and that gives us 144. Take note, that is not the length of the chord yet. That's just the length of X. The length of the chord should be twice that. And that gives us length of chord equals to 24 centimeter. Could it ever be easier? I don't think so. I'm very sure we are okay with this. We should be advancing now to look at how to solve triangles involving angles, making use of trigonometrical ratios, because so far you can see that Pythagoras theorem only handles sides. What about if we need to handle the angle? How do we operate this? From the next video clip, we're going to consider using trigonometrical ratios to solve right angle triangles. Thank you.